We've got to start right at the microscopic level to clear up a super common misconception. People use the words heat and temperature interchangeably literally all the time. But scientifically speaking, they're entirely different beasts. Picture a roaring campfire heating up a cool mug. Heat is the actual energy actively moving from the hotter object to the cooler one, and it's measured in joules. Think of it as the total energy you're adding to a system. Now, if you were to zoom way in on that mug, temperature, which we measure in degrees, is simply the measurement of the average energy of those dancing particles inside. So heat is the energy making the particles speed up, while temperature is just the thermometer telling you how fast, on average, they're dancing.
Now that we know exactly what temperature is, again, that average speed of the dancing particles, how do we actually measure it? Well, Celsius beautifully bases itself on water. It freezes at 0 and boils at 100. Simple, right? Fahrenheit places those exact same freezing and boiling points at 32 and 212. And then there's Kelvin. This is the absolute gold standard for science, setting water freezing at 273 and boiling at 373.
Here's a really cool detail to think about regarding the physical size of the degrees themselves. Because there are only 100 steps between freezing and boiling in Celsius, but a whole 180 steps in Fahrenheit, a single 1-degree jump in Celsius is physically larger than a change of 1 degree Fahrenheit. This bigger step size is what makes the Celsius scale so streamlined and, frankly, a lot easier to use for precise scientific work.
But Kelvin? Kelvin is special because it starts at absolute zero. I mean the literal bottom. 0K is the exact point where particles have absolutely no energy left and they freeze completely in place. Because the scale starts at this absolute rock bottom, there are no negative numbers in Kelvin at all, which makes complex scientific calculations, especially studying gases, so much easier and more logical.
Of course, to read any of these scales, you need a thermometer. When heat is added to a standard laboratory thermometer, the liquid particles inside gain energy. They spread apart and they physically climb up the tube. But here's the catch. You must read that line exactly at eye level. If you look at it from an angle above or below, it actually distorts the line. That's a mistake scientists call a parallax error, and it'll give you a completely false reading.
And hey, you definitely wouldn't want to use one of those boiling hot lab thermometers on a person. Lab thermometers are built tough to handle the massive extreme temperature ranges of chemical reactions. Medical thermometers, on the other hand, operate in a tiny, incredibly precise range, usually just 35 to 42 degrees Celsius. This is strictly so they can safely and accurately check if you're spiking a fever.
So how does adding or removing heat physically transform the stuff around us? Well, picture a solid block of ice. The particles inside are locked tightly together. But as you pump heat into it, you're basically feeding those particles raw energy. They start violently vibrating until they physically break out of their rigid structure, melting away into a flowing liquid puddle.
But, guys, here is a truly wild fact you've got to remember. If you stick a thermometer into a bowl of melting ice, it will read exactly 0 degrees Celsius until every last piece of that ice is totally gone. Even though you are actively adding heat to the bowl, the temperature itself doesn't budge. That's because all that heat energy is entirely consumed by breaking those rigid crystal bonds of the ice, rather than making the newly freed liquid particles move any faster.
Now, once all the ice is completely melted, the temperature can finally start to rise again. If you keep heating that liquid water, you're giving those particles even more juice. Eventually, they get so incredibly energized, they just completely fly apart and escape right into the air as a gas. That energetic escape act is exactly what we call boiling or evaporation.
And, cooling does the exact opposite. It's simply the removal of that energy. Cooling a gas forces the wild particles to lose their energy, slow down, and huddle together into liquid drops. We call that condensation. Cool it even further, and they slow down so much they lock right back into a rigid, freezing solid.
This actually brings us to the invisible force that's going to solve our mountain cooking mystery from the beginning. See, boiling isn't just about heat. It's a literal battle against the air pressure pushing down on the pot. Think of air pressure as a heavy, invisible lid. Under high pressure, particles need a ton of heat energy to push through that lid and escape. But under low pressure, that invisible lid is way lighter, making escape much, much easier.
Let's put that into perspective. Down at sea level, you have the heavy weight of the entire Earth's atmosphere pushing down on your pot of water. It requires a full 100 degrees Celsius of energy for the water particles to finally boil and escape. But if you climb a high mountain, there is literally less atmosphere stacked above your head.
Because that pressure drops significantly, it becomes way easier for those water particles to break free. The water doesn't even need to reach 100 degrees to boil. It might start bubbling and turning into gas at just 90 degrees Celsius, or sometimes even lower. Boom! Mystery solved, right in front of us. Up on that mountain, your water is boiling. It's violently bubbling away in the pot for sure. But because of that low pressure, the boiling water is only 90 degrees, not 100. And since the water literally just isn't as hot, it takes significantly more time for your pasta or potatoes to absorb enough heat energy to cook properly. Kinda wild, right? Boiling definitely does not always mean 100 degrees.
These concepts dictate almost everything we do to survive. A thermometer tells a chef their meat has reached a perfectly safe temperature, completely preventing foodborne illness. It allows doctors to spot a dangerous fever before it gets out of hand. It helps meteorologists forecast weather so farmers know exactly when to protect their crops from frost, and it lets pilots understand the exact air density they need to take off and fly safely.
We've seen how heat, temperature, and pressure silently pull the strings behind the scenes. So I'll leave you with this final thought to chew on. If the microscopic dance of particles quietly dictates everything from the physical state of water to the exact time it takes to cook your dinner, how many other unseen scientific forces are secretly shaping your reality right now?